In this lecture, we're going to kind of do a sneak peek, and I call it sneak peek because we're going to jump ahead into a more advanced subject, but not thoroughly exhaust it. We just want to introduce it and give you a sneak peek and kind of whet your appetite or pique your interest. In this lecture, this sneak peek, we're going to look at requested packet interval. As you know, the I/O modules, all modules on the backplane 1756, have an RPI, requested packet interval. Because remember, those modules communicate with the processor on their own hook, so to speak. Not entirely. Let me explain. When you add modules to the backplane, the virtual backplane in your project, in other words, you have to add all those modules before you can use them in programs. You select an RPI. Now you may select it by default, meaning that you didn't touch it and it came up, it was 20 milliseconds and you left it 20 milliseconds. But in a sense, you selected it by default, and you can lower it down to 1 millisecond and you can increase it way up. And the RPI is you configuring the I/O module to tell it when you want it to communicate. How often do you want it to communicate? The default is 20 milliseconds, which means an input module every 20 milliseconds will broadcast on the backplane. Now, it's broadcasting because it goes the length of the backplane, but it's actually only going to be received by the processor. The processor will take that information and place it into memory. And it can do that in most cases while it's actually executing the program, the ladder logic diagrams or whatever program language that you used. So that's why it's called requested packet interval. Now there are some exceptions to that. That's why the R is on there, requested. There's no guarantee that it's going to be exactly 20 milliseconds. But we're going to play with that a bit, and that's why we call it a sneak peek, because you don't really, you don't need to know that right now. Let's do it. In the manual, roughly page 105, 106, something like that, you had something called Sneak Peek 2. When we do a sneak peek, we're kind of looking at more advanced subjects, but we're not going to exhaust our knowledge on them at this point in this volume. Our goal is to make this a 4-volume series that basically goes through the same instruction set, the same sequence that the Complete PLC Learn series manual did when we were doing that with RSLogix 500 and a MicroLogix or SLC 500 processor. And that's why we say this is beginner, because we're starting right from scratch, but we're using the Logix engine instead of the older hardware platform. This is a sneak peek at a more advanced subject. You may have noticed the messages in the errors panel, but we have discussed those. I had you address the same memory location, local 10 data 0, with 2 different OTE, output energized instructions. Although there are scenarios where this is acceptable, this is not one of those instances. I had you do this to demonstrate the last man wins idiom in ladder logic diagrams. What you witnessed in this last lab project, the intermittent state change of the output LED device, would not have happened with SLC 500 or MicroLogix using RSLogix 500, the older platforms, or with PLC 5 as far as that goes, or PLC 2, or Card Logic, however far back you want to go. The older platforms of controllers, referred to as PLCs, had a single sequential execution of I/O scan and program execution, controller housekeeping, communications, etc. Then output states transferred over the backplane to output modules, input devices collected across the backplane from input modules, execution of program, scan of rungs top to bottom, left to right, reading bits in memory and writing to the state of bits in memory. Not in any particular order. I'm not giving you this in any particular order. I'm just telling you that the older platforms cannot chew gum and walk at the same time. So picture yourself chewing gum. You walk a few steps, stop, chew the gum. But you're not allowed to do both at the same time. I know that seems idiotic, but that's PLCs, that's how they work. They can't chew gum and walk at the same time. And they are very synchronous. However, we are using the Logix engine now with RSLogix 5000. Within the list of controllers, processors, that are supported with a version of RSLogix 5000, and I have probably mentioned before that RSLogix 5000 has went through many major rev levels since it was introduced back in 2000, 2001, something like that. Maybe it was 1999. But I do remember going to Automation Fair in Nashville, Tennessee, and being introduced to it and thinking, holy moly, I'll never learn to do that. That looks crazy. If you're an old timer and a geezer, or an old geezer, or even a super geezer, probably not an ultra geezer. Anyway, if you're a geezer and you're learning RSLogix 5000, you probably identify with that reaction when you first see these tags, when you first see the database compared to the 500 MicroLogix 5 databases where all the variables were pre-declared. You didn't declare any variables. Not like here where we create our own variables, pointers, variables, tags. They were all predetermined for you. So really, RSLogix 5000 is more reflective of how computers are programmed than the older RS500, RS5 platforms were, where all the variables were declared for you. You could instantiate a type of variable like a B3, T4, C5, R6, N7, F8. You could expand those out to X number of elements, or you could even create another couple hundred more data table files, but they still had to be in the exact same structure. Whereas with 5000, the sky's the limit. Your imagination is the limit here. Some people have gone nuts with it and created some code with tag names that just baffle you. That did they really think anybody was going to have to look at this code when they were done? But nonetheless, RSLogix 5000 is a great thing. As I said, this is a sneak peek and not an exhaustive dissertation on the subject. Hence, we will only touch on a single detail, I/O tasks, because that's what we're dealing with here. Although I'm using a 1769 Compact Logix with version 20 of RSLogix 5000. Remember, RSLogix 5000, the version level of 5000 and the firmware level of your processor have to be identical. So if I go look at properties on my processor, lights on, no one home, come on. Well, we'll double click on it. Or we could have gone up here and clicked on the controller properties. Remember, I'm using RS-232 or a 38.4 baud rate simply because that's what most of the learners, you folks, are probably using because those processors are much less expensive than those with Ethernet. I would that everybody had an Ethernet processor. Although I own many Ethernet processors, I want to feel your pain. So I'm suffering here with a speed just like you all. See, revision 20 for that controller. The revision level of this software that we're running is also 20. See, V20. CPR, Coordinated Product Release 9, Service Release 5. What I was pointing out was that RSLogix 5000 has been through many major rev levels since 2000. So that would be 15 years ago. RSLogix 500, we'll just say slick 500s, in 15 years had maybe 2 major rev level changes. Even though they might be up to 6 point something, the firmware in the controller has only changed a couple times in SLIC 500. And you can tell this by looking at the labels on the controllers. So my point is, in 500 or 5 land, the landscape did not radically change very often, maybe once every 5 or 6 years. With RSLogix 5000, and remember that the rev level of the controller has to match the rev level of the software, the app that you're using, what you're looking at right here. They have to be the same. That has changed for the most part every 9 months since its inception. That's kind of a rabbit that you have to chase continually with the Logix engine platform. It's not a big deal once you're used to it, and being able to flash the firmware on a processor or an I/O module is very simple. So it's not as convoluted as it sounds. Nonetheless, so we have version 20 of 5000 and the controller. At the moment, we're only interested in the I/O task. Now this is on page roughly 106, 7, 8, 9, something like that in your manual. So you're going to have the manual to go along with what I'm discussing. If you're just looking at the screen, you're going to miss something. So you need to open your manual to that page and find the pictures of the different platforms. If you're using a 1769 compact Logix, like I am using, what you see in front of you, there is one CPU in that controller. If you're using a 1756 L6X control Logix or 1768 compact Logix, and I do have 1768 compact Logix that I use for doing motion, then you have 2 central processing units. You have a backplane CPU and a Logix CPU, whereas the 1769, one CPU does both the I/O task and the logic task. In a 1756 L6 or 1768 compact Logix, you have 2 CPUs. If you're using 1756 L7X, that's the newest, or I should say the most advanced of the control Logix processors, you also have 2 CPUs. So 2 CPUs is better. One of them concentrates on the backplane, the other concentrates on logic. So your continuous task is more continuous with the 1768 and the 1756 L7. If you have the new compact Logix, they've gone back to one Logix CPU, and if you're using soft Logix, well, personal computers only have one. Well, they have dual processors, but the way that soft Logix 5870 is structured, it's as if you only have one Logix CPU. Of course, we know that that rides on top of the Windows operating system, and there's clever things that you can do to make it execute very fast. The fly in the ointment of soft Logix is the personal computer. I don't care whose personal computer you buy. I don't care what brand it is. Even if it's a rack mount card system that runs Windows 7 Pro or whatever operating system you're using, inherently the hardware and the firmware used in this hardware platform, personal computers and like computers, is not as well massaged, is not as well tested, is not as well burned in as a programmable logic controller or programmable automation controller. The programmable controllers, the testing that they go through, especially regressive testing, it's incredible, the kind of testing that they go through. No one puts a personal computer through the testing that a PLC goes through. Now remember that a programmable controller only runs a limited amount of applications. You could say basically one application with a variety of nuances in that application, whereas a personal computer has to be able to run almost anything. If you have to be able to accommodate everybody, then you have to leave it more wide open, and therefore it's more prone or more vulnerable to crap. Can't think of any other way to put it. Okay, now we're going to play with our code a little bit to demonstrate some of this conceptual stuff that we've been discussing about scam time, requested packet interval. Let's back up to the first hint of the cause in the earlier lab project. I had you open up the properties of the main program. Right click on main program, properties, go to monitor. We want to monitor the main program. And here's what we see for our typical program scan. You see it does jump around a little bit, but basically it's 20 microseconds. Resetting the maximum, now you see the maximum that we've had in the last couple seconds is now it's 188 microseconds. But you see this is an active dynamic monitoring of the actual scan time for that program. That means that the two rungs of logic, these two rungs of logic execute every 20 microseconds. You could say one rung per 10 microseconds. Now that's not really totally true, because there's more going on than just executing those two rungs of logic. There's some background tasks and some housekeeping, but nonetheless, it's going through the complete scan every 20 microseconds. I had to go to the I/O module, go to properties, and go to connection. By the way, if you want a more detailed discussion of this subject, refer to publication. I'm not going to read the publication number, it's too long. It's in your manual on roughly page 110. Now, depending upon the hardware version combination, i.e. pre-version 18, you may not experience the anomaly with the intermittent outputs. Remember that we're up to, I think, at the point that I'm recording this, I think we're up to major rev 23 or maybe 24. It means since 2000, 1999, whenever the Logix engine kicked off, we've had 20 some major revision levels. So things change. And another thing that you may not be aware of, and I can't remember if I mentioned it before or not, but we were talking about the different chipsets, microprocessor chipsets. And when you have a controller, you don't just have a CPU, you have a set of chips that allows us to have all the features that we have. Well, chipsets, their availability for a particular chipset does not last forever. Periodically, whatever chipset that Rockwell Automation is using for the Logix engine platforms, ControlLogix, CompactLogix, DriveLogix, etc., the manufacturer of the chipset may call up and forewarn Rockwell that they're going to discontinue manufacturing of that chipset, and that Rockwell needs to put in their final order for that chipset. They get their heads together and they come up and say, all right, we're going to obviously have to redesign the hardware for a new chipset. How many chipsets do we need to continue to produce these processors until it's been redesigned with a new chipset? So at the same time, they've already got engineers working on picking out a new chipset to go with. So they call up Intel, AMD, whoever, I don't know who makes their chipsets, and says, we need 20,000 of those. And then that chip company comes back and says, a day or so later, says, well, we can give you 12,000. That's as many as we can run. Well, at that point, it's cast in concrete, more or less, unless they can find that chipset surplus from some other company that bought some. But the point is, at some point, they're going to have to redesign that processor with a new chipset. And guess what? That alone is a cause for a major rev level. So not only are there new major rev levels to give you more features, because from day one, we as customers have hounded them for new and better features for the Control CompactLogix platforms. That's why when I say pre-version 18, that should clue you in that it's not just a matter of they come out with some improvements for RSLogix 5000. They have to deal with whole new chipsets. The Compact Bus Local RPI, that's Compact Bus Local, that's right down here. That backplane right there. Requested packet interval defines the frequency at which the controller sends and receives all I/O data on the backplane. There is one RPI for the entire 1769 backplane if you are using pre-version 18 1769 L3X family processors. It's not just pre-version 18, which means in version 18 it changed. Version 18 was different than 17 in that respect. It's not just the version, but it's also the family of processors. Let us turn the two pieces of data that we just exposed from our live project, scan time and requested packet interval. While observing your intermittent output, change the RPI on that output module to 5 milliseconds. I immediately had you change it to the fastest, but first change it to 5 and then watch the behavior. So I'm going to change that to 5, apply. It gives me a warning. We're not running the machine, we don't care. Now, you can't hear it in the background. See, the scan time is still the same. It did not change the scan time. The only thing that we effected was that we effected a different asynchronous interaction. So now my output is going nuts over here. Now you can't see it here because this screen from my laptop via its chipset, RAM, I/O ports, USB cable, RS-232 adapter out to the L31 processor, it can't keep up with what the processor is doing. Never rely on what you see on the screen for intermittent or high frequency changes of state. What I hear now is a more rapid alteration, which means that if it takes 20 microseconds, I just saw 22, 28, to go through the scan, and I'm updating I/O every 5 microseconds, I have an even greater chance of hitting it in between these two rungs. Now, if I was doing it every 30 microseconds, the RPI, then I'm liable to not land in between these two rungs very often. Then I had to change it to the fastest. Back to our properties here. Connection. Now I can make it 1 millisecond. That's as fast as I can make it. Again, this is a standard warning that would cover all possible situations. We're not running the machine, so it's not going to hurt anything. But if you were doing this online with a processor that was running a sensitive machine process, you would not want to do this. I just saw the jump to 106 microseconds. So you see, there's a lot of things going on in the background that you really don't know about. Because I'm doing it let's check to see if it took, by the way. That's interesting. Doing it every 1 millisecond, that means I'm doing it at least 20 times. Our scan is still roughly, I see it's all over the place now. Something about making this 1 millisecond has definitely affected some things that we're not going to explain here. But the main thing I want to point out is I'm at 1 millisecond now, which means that my I/O update is definitely falling between these two many times. But it's not going from on to off or off to on once in between. Every once in a while we might see it flicker. I'm not seeing it flicker at all. Oh, there it just did. But I'm not hearing it because the state is changing for such a short period of time that the relay contacts don't have time to energize. If I look at the output LED on the I/O module, I may or may not ever see that output flicker on. Because remember that even though LEDs are very, very, I just saw a tiny flicker. Even though they're very responsive, it's not like an incandescent light bulb. An incandescent light bulb, you'd never see it come on because it can't heat up that fast and cool down that fast. LEDs are fairly quick response. I did see the LED flicker on that output once, but it was so light and quick that I really wasn't sure that I was lying that I saw it. I guess, nonetheless, you see what's going on here with the RPI and the scan time. 5 milliseconds, the intermittent state was at a higher frequency and still discernible with the output LED device. But at 1 millisecond, I could hear the relay output chattering without any visible state change. Now, I don't have my relays chattering right now, but the output is on all the time. But remember, I also flipped my I/O. So now I'm going to put this back. I'm going to open this up a little bit here, and I'm going to drag this down to here. Finalize all edits. Okay, now I can hear it chattering, and I can see the output flickering on and off. I had forgotten that I had flipped these two rungs just for fun back in, I think, in the previous video, and I forgot to flip them back the way to the sequence that they're at in your manual. So it should not have caused any confusion. However, it is interesting, and I have discovered this by accident, that with these rungs flipped, 1 millisecond doesn't seem to be as big a problem as 5, or we're going to go back to 5 since we did that with the rungs, the order the rungs rotated or flipped. I don't know if you can hear that chattering in the background, but the relay is flickering on and off. If we were to further increase the requested packet interval, eventually you would not notice this behavior, but it is still a possibility. And keep in mind that destructive bit programming is highly frowned upon in the industry. You would not ordinarily have two OTE instructions addressing the same bit memory. So let's bump up this to the RPI to, say, 750 milliseconds. Okay, now it's unlikely you're going to notice it. Every 3/4 of a second, because remember our RPI, requested packet interval, is now at 3/4 of a second, 750 milliseconds. That means every 750 milliseconds, 3/4 of a second, the I/O is going to update, which means the hand is faster than the eye, maybe. I might even be able to operate a push button fast enough that it misses that state change altogether. We're not going to fool around with that. But every 750 milliseconds, 3/4 of a second, there is an opportunity for the I/O update to fall in between rung 0 and rung 1. But that's every 3/4 of a second. As you go up in RPI, the possibility of that happening is less and less. Okay, so what does all this mean? Really, this is just a sneak peek. We're just kind of poking around into the dark corners of RSLogix 5000 and the Logix engine. And the more you poke around, the better comprehension and intimacy you have when writing programs. In the manual, roughly page 111 or so, I have a diagram that shows this relationship between the RPI and the scan time. And it states every 11 microseconds, the logic tells the bit memory to change state from on to off or off to on. So if you're executing these two rungs of logic here, every 20 microseconds, then every 10 microseconds or so, this logic is telling that bit that it's in a different state. At 20 milliseconds, the I/O task updates the output module with the current state of that bit. If our RPI is set at 20, we'll set it back to 20. Okay, RPI is set back at 20. And we do have the chattering. We do have the intermittent behavior. And you see that the scan is not exactly 20 milliseconds. If you're splitting hairs here, what we used to call nitpicking. If you're nitpicking, you could never get the scan time to line up with the RPI, so there was not this problem simply because the scan rate is not consistently at one fixed rate. There's other things going on in the background. You can see that no matter what you do here, the I/O update is going to fall in between rung 0 and rung 1 once in a while. Even with 750 milliseconds for an RPI, it's still going to happen once in a while. And that could mess up your program. I'm listening to my relay chatter over there. It goes for a long time, and then all of a sudden it hits 4 or 5 of them in a row. So you can see that as the last scan length changes, so does the flickering. That's enough of the sneak peek. Get on with what we're actually learning.